Okay, let's look at a couple of more examples. So following from the previous video, same directions, that says find the hydrostatic force on this vertical plate submerged in water. So as before we said, we're going to set up our axes first, and then we're going to deal with our rho g dA and fill the pieces in as we go along. So again, due to the symmetry of this region, I think I'm going to put my axes right through the middle at the surface of the water. So there's my origin. This is an X and this is a Y, and again, downwards direction is positive. I'm going to go look at one slice and see how I can fill in the pieces of my integral. So again, since I chose to put my axis at the surface of the water, the distance this blue slice is below the surface of the water is just a vertical distance. Take it back to your axes touching the origin. So it's just a Y distance. So distance of the piece below the surface of the water is simply Y. And then for my area, I have to do length times width. So this guy I will call L, and this thickness is a delta Y, a vertical thickness. So my length times width, I guess my length all the way across, since I made it in the middle, is 2L, length times width. The whole length is 2L, and then the width is a delta Y, so I'll put it as dy in my integral. And I will figure out what L is in terms of Y. And it looks like I can again do similar triangles here. So if I take this half piece, this triangle out here, this distance is what they label to be 5 meters. And we should also know this. I'm not drawing it accurately to scale, but that's half of the 4 meters that I had all the way across. So that's 2 meters. I'm interested in finding that little L piece. And so it would be useful for me for my similar triangles to be able to find what this is, I guess, so that I can do all of 5 is to 2, as this little red segment is to L. And again, my goal is to put L in terms of Y. So all of 5 is to all of 2, as the red segment is to the blue L that I'm looking for. Now the red segment in my picture is actually rather easy. This little red segment is the segment that's touching my origin. It's the same thing as that D that we found, which was simply Y. So that segment is a vertical segment touching the origin, so to Y units down. So that's really just Y. So 5 is to 2 as Y is to L. Let's cross multiply and solve for Y, which is going to be, I guess, 5/2 L. Actually, I don't need Y, I need L, right? So let me solve for L. L is 2/5 Y. So I can go put that in here now. So we're almost there. Remember, the entire length of the blue piece was 2L, and I found the L to be 2/5 Y. I have my dy for my width. Now let's go look at where the blue slices are made. The blue slices are made all the way from the tip to the bottom, and based on my axes, the very top happens to be 0, and the very bottom, pretty easy, is 5 units below. So it looks like the blue slices are made anywhere from 0 to 5. Those are my limits of integration. So the force, rho g, what units am I in? If I'm in meters, I'm in the metric unit system. So 9,800 for the rho g part from 0 to 5. And I have 2 times 2, I guess, 4/5 y squared. dy is what I'm looking at. So we could easily integrate that 4/5 y cubed over 3 from 0 to 5 times 9,800, and that's going to end up being, approximately 326 1,667 newtons for the force, hydrostatic force acting upon that plate. So that actually wasn't so bad. All we did was set up our axes and deal with similar triangles. Okay, so same directions here. Find the hydrostatic force acting on this vertical plate. And this shape looks like it's a semicircle. And first thing, again, we're going to set up our axes. And then we're going to figure out our rho g dA business. Now, in the previous problems, I would set up my axes at the surface of the water, which I can easily do here, but notice if I do it at the surface of the water, this circle that I'm imagining, this full circle, will be shifted. I think I would rather deal with a circle that's centered at the origin. So instead of putting my axes and using symmetry right smack in the middle at the surface of the water, I think instead I'm just going to make my axes smack in the middle of this, so that I can use an easy equation for a circle relating x and y. Again, I purposely chose it that way because I would rather deal with a non-shifted circle than a shifted circle. If you set up your axis at the top, you just use a different equation for your circle. It'll be shifted with the center being different, so it shouldn't change things, but this will probably make it easier for me if I set up my axis this way. Okay, so let's go make a slice and see what happens. So I'm going to make a representative slice in my picture, and I'm trying to fill in the rho g dA business. So the first thing I'm going to do is figure out the distance from the surface of the water. So here's the surface of the water. Here is the distance to the slice I made, d. So notice if I take the d back up to my y-axis, it's not going to be touching the origin. It's a distance up in the air dangling. It's not touching the origin. So if I look at that distance, notice it's up in the air, not touching the origin. Well, what is that entire segment from here to here? If this is a semicircle that's 10 feet across, this must be 5 feet, right? The radius must be 5 feet. Therefore, this must be 5 feet. So up to here, I must have 5 feet. And then I had another 2 feet that it's submerged under. So it looks like the distance all the way to the bottom is 7 feet. The entire distance is 7 feet. I'm interested in the distance dangling up in the air. We do know that if we needed this distance, that distance is simply touching my origin, and it's a vertical segment y. So that's a vertical segment y. The entire thing is 7 units. If I need the leftover, which is the blue d business, it must be all of 7 minus that little y. So it looks like the distance beneath the water for that segment is 7 minus y, which is different than the ones we've done before because we've chosen to put the axis at the surface of the water. But even if we don't, nothing really changes. I just have to analyze the picture, and that distance d is dangling up in the air, so it's all of 7 minus that y. So we're done with the d. Now I'm going to have my length times width. So I'm going to call this guy length, and then remember to double it. And remember, this is a vertical little delta y for my width. So for my area, I basically have 2L, which is the entire length, times the width, which is delta y. So 2L times delta y, and I'm going to call that a dy in my integral. Now I need to figure out y, or L, in terms of y. And we know that because of the way we made this axis setup, that I have this relationship between x and y. X squared plus y squared equals, if it had a radius of 5, equals r squared would be 25. So again, I repeat, the relationship between x and y, I don't need to look at similar triangles or anything else. X and y relate to each other with this equation of a circle that I chose to center at the origin. So if I need to figure out what this distance is, remember this is L that I'm interested in. If I need to figure out what that horizontal distance is, I repeat, horizontal distance, and if I bring it back to my axes, that horizontal distance will be touching my origin. So if it's touching my origin and it's a horizontal distance, it's simply nothing but x. So that little distance L for my length, or for half of that whole thing, is simply an x value, nothing but an x distance, which means I need to isolate x here to figure out what x is in terms of y. So x squared is equal to 25 minus y squared, and x is plus or minus 25 minus y squared. I'm just looking at the right piece, so positive x is what I'm going to choose. 25 minus y squared is that distance L, because all it is an x. So that's L. And so it's 25 minus y squared, and I can go put it back in there. So force is equal to rho g, since I'm dealing with the US system in feet, will just be 62.5 for the weight density of water. My distance was 7 minus y, and then I have 2 times the length that I found here, which is 25 minus y squared dy. Only other thing that remains is, where are my blue slices appearing based on my axis? So blue slices all the way from the bottom to the top. So the bottom is a y value of 0. And then I keep slicing, oops, okay, we're back. I keep slicing the blue pieces from 0 to the very top. Here is where my shape ends, and that's the top, which is 5 feet, because the radius was 5 feet. So my limits of integration go from 0 to 5 in this case. Let's pull the 2 outside. So force is equal to double the 62.5. That gives me 125 from 0 to 5 of 7 minus y square root of 25 minus y squared dy. Now I can do this using my TI to get an approximation for the force. So we'll do that, and then I'll quickly talk about how you would deal with that by hand also, because you should know how to do that by hand too. So I put this piece into my TI, 7 minus x times the quantity 25 minus x squared dx problem from 0 to 5. I got that, and then I multiplied the result by 125, and it looks like the answer is 11,972 pounds approximately. Remember, we're in the US system, so pounds is the units. So we approximated the force due to water using our TI calculator. Now let's go quickly look at how you would integrate this by hand if needed. If I needed to do this by hand, I would need to distribute this into both pieces and end up looking at 2 separate integrals. So pull out the 125, deal with it later. 7 times that radical dy, and then minus another integral y times that business dy. Now this is going to be an easy u sub, because if I let u be 25 minus y squared, then my du will pick up that y dy that's sitting around there. So for this piece, I will pull out the negative a half and put it in the front, and that'll become a positive a half. When y is 0, u is 25. When y is 5, that's 25 minus 25, y is 0. And that's square root of u, and this piece had been picked up with my du over negative 2 anyway. So then that's just an easy integral to deal with. For this guy, since I don't have a y like I did here, it looks like I have a radical and squares involved, so I must be doing a trig sub. So it looks like y must be 5 sine theta, dy is 5 cosine theta d theta, plug in your dy, pull out the 7 outside, and you have 25 minus 25 sine squared. Change your limits of integration. If y is 0, what angle has sine of theta equals 0? That theta has to be 0. And if y is 5, divide both sides by 5, sine of theta equals 1, and that angle is pi over 2. That gives me 5 cos theta when I use the trig identity. But I pull out the 25, 1 minus sine squared goes to cosine squared, popping out a cosine. Multiply in 25 cosine squared theta, and now I have to use power reducing. So after this point, I pulled out the 25, 175, and power reducing turns into 1 plus cos 2 theta over 2. And from here on, you should be able to handle it, and you should be able to handle this as well. Add the 2 pieces and multiply the 125 that you saved outside. So from here on, it's just a simple theta over 2 and sine 2 theta over 4 it looks like.